Yeah.
Kind of foot to one side and foot to the other side.
Yes, it's kind of like dancing between the two fields. I'm truly honored to be here, and it was really nice that Fadil approached me for being a speaker here, and further, I'm actually going to be around for the whole day. So I welcome you to come after the talk, and I would love to answer any question that you may have regarding the talk or just in general about 3M careers data science. Before I start the talk, I would like to give a little bit of a background about myself. So I have a PhD in computer science, where my thesis was like developing machine learning algorithms with applications to computer vision and neuroscience. And what a lot of you probably don't know is that before entering computer science for PhD, I was trained as a physicist with a bachelor's and a master's in physics. And the reason I think I landed myself in data science is because I was really interested in solving very interdisciplinary problems. And back in 2009, data science was not as hyped as it is today, but I think everything turned out to be good. So just a little bit background, because this talk is not really technical as the previous talk was, but I'm going to build on a lot of things that the previous speaker alluded to in terms of like dimensionality issues with the data and stuff like that. Feel free to stop and ask questions in between as well. So first thing is that what does data science means to you? And this question is really interesting because it depends whom do you talk to and what kind of answer you will get. Because even like as of now, with so much going on around data science, there is not one general definition that people usually agree to. And depends who you talk to, you will learn what their perspective about data science is. And I'm going to use this occasion to actually go over what data science means to me. And I'll start using this Venn diagram, where this Venn diagram is actually really interesting because it's very simple, but it also highlights the highly interdisciplinary nature of data science, where you are working with different kind of applications, neuroscience or something else. You're using your computer science tools and mathematics and statistics to try and test hypotheses and report result or change your model and answer interesting questions. While we can go much deeper as to how the process of data science iterate over different subsets of this Venn diagram, I want to focus on the first important thing, which is what is the important question that you are trying to solve? What is the right question? Because I think with the computer science and the statistics and mathematics being such a mature tool, there is a lot of hammer which have been already developed. And I think as a data scientist, it becomes really important that we focus on the important problems for better good, as Fadil kind of said in the introduction. And how I like to think about this worthy question is really a marriage of what to compute and how to compute. And I'm not going to focus too much on how to compute in this talk, because I believe that the audience is already pretty has all the tools that they need in terms of how to compute. So I'm going to focus on, most of the times, how to focus on what to compute. And that also entails talking to different people in the fields where your application is and gather information so that you can use that knowledge, you can leverage whatever they know about the field to kind of like develop better tools to solve the problem. And the way I have outlined this talk is I'm going to talk about my very first project when I started the PhD. It's not part of my thesis, but this project was really interesting because I could see the connection of neuroscience, computer science, and statistical methods to solve an important problem. And then in the follow-up, I'm going to also go over how this kind of like overview of data science has helped me in my career choice. I'm going to focus mostly on neurodegenerative disease, which are actually Alzheimer's disease, Huntington's disease, Parkinson's, ALS. And these diseases are known to kind of like cause gradual decay in the brain structure and the cognitive functionality over a time. And while studies have showed that different causes, different physical and biological events kind of cause these diseases, the problem is that early detection or early diagnosis of these diseases is very difficult. And the reason is because the person is, a patient starts having these changes much earlier before they become symptomatic. And even if when they become symptomatic, it's very hard to know from the very beginning whether the memory loss or the language issue that they are having is because of which particular disease here, because the symptoms are very similar in early stages. Alzheimer's disease is actually one of the very there is a great focus on Alzheimer's disease in the neurodegenerative research, and the reason is because as recent as 2016, the survey has concluded that within US, 5.4 million Americans of all ages are suffering from Alzheimer's disease, and the patient care cost could amount up to 100 billion each year. So, and that's why there is a lot of focus from NSF and NIH and other agencies to kind of like figure out how can we early detect subjects which are prone to develop Alzheimer's disease so that the cost of care can be reduced by early intervention. And the way people kind of are looking at this problem is very much like looking at all the data that they can gather about patients to kind of start modeling which ones are going to be developing this Alzheimer's disease in future. And one of the important biomarker that people have focused in last decade a lot is neuroimaging data, which is again this looking at the images of the subjects and learning patterns from these images to predict the possible Alzheimer's disease in the future. And one of the interesting biomarker is cortical thickness. What cortical thickness is actually is you kind of have a scan and then you rip off all the skull and other stuff from the outside, and what you are actually marking is the boundaries between white matter and gray matter. And by opening the brain of people who died because of Alzheimer's disease, researchers have found that gray matter loss in between these regions is actually pretty common in Alzheimer's disease. So the hypothesis is that if you have Alzheimer's disease, you start losing your gray matter in these regions. So that's why people are using this particular biomarker to see what kind of patterns do we have. We can start seeing much earlier before the full Alzheimer's disease is developed. So in the statistical framework, you can imagine that the framework is pretty straightforward, where you have an input signal, which is basically stripped through. You kind of like get after the whole pre-processing of the pipeline, you get a brain mesh. It's a 3D mesh. And then what you have as a signal is your cortical thickness value at every vertex in the brain. And this data is kind of like a process that in the beginning, they don't need to kind of like look at that how many vertices every brain has to have. Like they just take your scan and do the segmentation and things like that and pre-process, clean the data for you. So once you have the data, it is possible that your different subjects may have different shape and size of the mesh. So someone can have 10,000 vertices in their brain and someone can have 11,000 vertices. So there is no one-on-one correspondence, but nevertheless, you have this data. And the idea is that, okay, so this is a very highly attributed data. How can I extract different kind of features and put it through a classifier to predict who has Alzheimer's disease and who doesn't? And the early work mostly focused on focusing on certain regions which are known to get affected in Alzheimer's disease. For example, hippocampus has your memory function, and it is known that in Alzheimer's disease, most of the gray matter is lost in that particular region of the brain. So rather than worrying about the full brain, what you can focus on is just this region and extract features from that region and run it through the classifier. Or if you want to kind of grow your regions to capture different parts of the region, frontal lobe and as well as your hippocampus and ventricles and other stuff, the dimensionality of the data becomes a problem, which the previous speaker was anyways alluding to. And in that case, you can go about doing dimensionality reduction and feature processing to kind of pick which of the features are particularly of interest and which are the ones which are not very discriminative, so I should drop them. But as we can totally imagine that this process is too dependable on the sample size, and then at the same time it is too intensive. So that kind of caused this problem that these models, while the accuracy may be really good because you are doing too much feature engineering, they may not be easily extensible if you want to use this marker with other information. And I would like to go over actually a simple example because that kind of like helps. I like simple examples. Let's just put it that way. Let's imagine that rather than a 3D brain, we have a 1D brain. So we are only measuring the cortical thickness along one line. So my brain is flat, just simple one line, and the cortical thickness at different points on this 1D brain is given by blue lines. And with a little bit of a smoothing, I can imagine that the red line is a good representative of my cortical thickness of my 1D brain. And as I was talking about that, now the options are either I kind of parameterize this red line and use those parameters to kind of like look that if there is a discriminative power in the parameters, which I use to parameterize this red line across different subjects, and it has the power to tell me who has Alzheimer's disease or not. Another very simple way to go about is that, okay, I'll do I co-register all the 1D brains that I have in my data, and then do a pointwise comparison of what is the cortical thickness of different subjects, and use this to kind of like build a kernel to use in classification. But as you can imagine that if from the very beginning everything is not co-registered, in the process of code registering by sampling, undersampling, or oversampling, we may lose subtle information about the brain changes. And this becomes really important when you are trying to actually look at the patients which are not symptomatic. So that means there is something happening, but it's not as drastic that if you kind of like bring in a lot of feature, you may actually obscure the particular signal that you are trying to capture. And that happens a lot. That's why you don't want to over smooth, you don't want to kind of like go from one space to another a whole lot, and that's important actually. So what we proposed back in 2012 is kind of like, after talking to our collaborators who were providing us a lot of like background about this problem, is that what they were telling us is that in people, the gray matter loss start without being specific to a particular region. So first of all, if we can build a machinery which can use the gray matter or the cortical thickness from the full brain, it would be really nice to see, because people start losing gray matter almost everywhere in the beginning, and then as the disease progresses, it starts showing much severe effect in particular regions only. So that was first thing that we learned. And then another idea was that because of the dimensionality issue of this big data, which is like 10,000 vertices per brain, the idea was to kind of stay away from the dimensionality issue. So what we wanted is a precise characterization of this phenomena, where in a global sense you are losing your gray matter, and you want to predict which of them is attributed towards AD and which of them is just normal aging, because in aging also you lose your gray matter, but not in the same way. So what we proposed is actually look at derive its representation using what we call persistence of topological surface features. What it means is that, going back to 1D example, is actually this is a 1D signal, but rather than using all the data points here, why don't we kind of like represent how this signal is kind of filtered and how the homological classes are giving birth and then dying. So what this means in the signal filtration framework is that we start looking at the function value, and then as soon as we saw one critical point, that's the birth of a homological class. And as we go on in filtration, we see some more births, but after a point, we start seeing some death. So we pair the in a certain way from computational geometry, we start pairing these birth and the death of homological classes to build a 2D representation of this one-dimensional data. Now, you can imagine the brain is not 1D, so the data is actually a 3D mesh. So, without getting into too much of a pre-processing of taking this very complex manifold brain, what we did is like we extended the idea of this signal filtration on actually the actual manifold of the brain, but it still ended up with a 2D representation of the whole brain, where every point here is looking at that the persistence of a homological class that was given birth and then it died. Now, you can imagine if there is too much noise in the data, you will see a lot of like minima and maxima in the signal. In that case, what you expect is to kind of have a lot of points being generated here. But when a particular critical point stays open for too long, then it's going to have its representation encoded at this point. So it also allowed us not to be too worried about smoothing of the data, because we didn't want to over smooth. We kind of took care that if it's too much noise, it'll just pile up here and it won't be discriminative. But in this 2D representation, there was no issue of like of having a lot of dimensions. So we believe that a statistical framework will deal with that, because we had like enough data to begin with. And once you have this precise characterization, for example, a subject is, rather than being 10,000 vertices and cortical thickness, now became just a 2D representation of their homological class, of persistence of their homological class. And after doing some processing in terms of like some smoothing, generating a new representation, and then just vectorizing it, allowed us to use this new representation in a classification framework much more easily. We kind of like, these are some results. So what I'm showing you here is actually of all the 2D representation that I generated for Alzheimer's disease patients, I look at their mean, and then I also looked at the mean of all the control subjects. And by just subtracting these population means, we were easily able to see that there are striking differences. Now, what I am showing in these two places is because we are analyzing the left brain and the right brain. So the representation was like for different hemisphere, it was different. And this is the p-values in the log scale, where it shows that at a lot of places, this representation was statistically different between the two groups. So that was part of the statistical analysis. In terms of classification accuracy using the 10-fold generalized method, we found that the accuracy was 75%. And I would like to mention that in terms of if we go after accuracy, there are papers who have showed with a lot of intensive feature engineering that you can get up to much higher accuracy, 80% or so for the same data set. But what we found is that when you kind of like use this simple representation, the 2D representation of persistence, along with these extensive methods, the total performance, the performance of the combined model was even better. So what does it inform? It informs that the two different representations are actually bringing some information which one specific model was missing. And that is the power of data fusion, that we want to kind of look at the different modalities of the data in a way that it kind of like compensate for what we are missing in one modality. And because of its concise representation, it allowed us to kind of like, it becomes very extensible to use with any other view of the data for the same patient. So that was like a interesting project. And as I said that this was like my first project, and I was really excited in terms of like learning how just listening to the field of expert allowed us to look for the best method that fitted our assumption, our hypothesis about how the gray matter was decreasing in the brain of people who are going to develop Alzheimer's disease. Now, as I said that as a data scientist, I was always interested in kind of like working on a very diverse problems. So when I was in the job market and I visited 3M, it was really interesting because 3M is one of the most diverse places that you can find probably, because they make so many different products. So I think the recent list is some 55,000 products. So that's why my now application space is like, okay, interacting with 55,000 products and looking into the problems from all over. So that, and when I interviewed, I actually told my director that it looks like I'm in an amusement park of interesting problems. So if you are kind of a person who kind of gets too bored too quickly with like one particular application, then it's fun to go to a place where there are so many different kind of businesses out there. In particular, we have 5 businesses which range from consumer, electronic and engineering, healthcare, industrial, and safety and graphics. And you'll be amazed what kind of products you use without even knowing they are 3M products. So for example, Post-it and Scotch Brite are one product that you probably use on day-to-day basis, but at the same time, in the safety and graphics, 3M makes all these retroreflective signs that actually help you drive in the night. And 3M is like is a place where to kind of like improve upon their existing products, and as well as to identify new products, they have teams of like different kind of field experts from the different fields, from computer engineering, computer science, to electrical engineering, to mechanical engineering, and whatever. Like, it's a full list. It's a kind of like a very conducive place to learn, to apply science to the life, and to grow. So I think it is really important for a data science to be interested in learning about new fields, because you can be master of your how to compute tools, but if you are not too much interested in listening to the problems in the application side, then it defeats the purpose of this whole data science philosophy. No, I have statistician. I kind of like have them here. So actually, in 3M, we do have a lot of statisticians. I probably missed them just because it's a long list, so no offense there. Okay, so I am part of the corporate research, and I work in this computational intelligence technology group, and we are at the forefront of bringing value to 3M products by using data science. We are actively acquiring and developing platforms for data science, as well as intelligent systems, where the data is coming from different kind of sensors, and then we are working in a lot of like computer vision and 3D data problems. So this is just to give you an example that it's not one particular thing. I think if you are looking into a very diverse place, you have to kind of develop a lot of different kind of platforms to digest the data to start doing some data science. So it's pretty diverse over there. And in the recent years, this particular lab is only like 4 or 5 years old, and within this time frame, we have launched a lot of interesting products. So for example, you are aware of using Post-it, and there was an app which was released, I think, a year or 2 years ago, which was Post-it Plus. And the idea was that once you are finished kind of like doing brainstorming with your collaborators, you don't have to worry about clicking a photo and not being able to organize if you thought that the process didn't go through in a certain order, but it was rather you want to kind of like save it as in a different order or share across other collaborators. And this app was named as, I think, the best app in the Apple device, and the editors had very good reviews. At the same time, we have had luck, very good fortune in kind of like using data science to launch better fitting products. And this is actually a very important thing, that when you are building products for very diverse population across the world, you want to kind of come up with the best designs that suit that particular region where you are selling the product. And this is called the Victory series of Superfit buccal tubes. Now, I want to take the opportunity to go more deeper in a particular division where I'm closely working, and that is the oral care division of 3M. And the division actually has up to 2,000 products in the oral care side of the thing. So whenever you visit a dentist, there is a high chance that they are going to use some 3M product on you. And one of the most common process that people go through is getting a crown fabricated for them. In a traditional sense, this process was very time consuming and intensive. And the reason for that, you have to kind of like give the impression of the tooth that you need the crown for, and that physical model kind of used to go around in different places until you get your final crown built. And then you have to come again in a second visit with the dentist to get that crown fitted. And at that time, I think business leaders in 3M were kind of debating as to how can we improve this whole experience and cut down the time that it takes for a dentist to put a crown on in your mouth, which is again kind of focusing on the real problem of the people and your customers to kind of develop a full pipeline to give a better oral care as well as improved experience. And this is from the business side. So it's always different how you think about a problem when it's for public good and when it is something important for the business. And there's no, I'm not going to go into the debate which one is important. So what happened is that 3M launched this true definition scanner, which actually, rather than taking physical impression of your tooth, it allows you to scan the tooth and store the digital impression of your tooth. And once that was established, it was very easy to kind of bring in the 3M material, which is known to produce most reliable crowns, to allow you to print the crown by the chair side of the patient. So you go there to get a crown, they scan you, and the 3D model is uploaded into the connection center. They kind of do the designing of it to the best fit, and then the 3D printer just print the crown in the dentist office using the new what we call is the card, the true definition card, along with the mill actually. And this reduced the whole second trip and waiting and not getting it fitted, because if the first time around you didn't get the right crown, you have to repeat the whole process. Now it is like you are right there. If something is not working, the doctor can look into it and then fix the model so that it is getting corrected right in the real time. Another interesting thing is that once you start building something on the data or digital data where you are acquiring it for one purpose, it's important to keep thinking and keep talking to the people in the field as to how to use this data that you are now generating and making it easier and easier to store to build further upon it. So for example, once we established the whole connection center and true definition scanner pipeline, we started collecting this data, which was now very easy to kind of like play with. And the idea is to kind of use this data and the technology to come up with better treatment planning for the patients, so that the doctors can review it in real time and suggest you what is the best course of treatment. At the same time, for different appliances, we now have like a lot of data stored in 3M Connection Center, where we can use it to build better fit other kind of like products that you may need. At the same time, because the digital data has this power of like being very accurate, the idea is moving dentistry from being qualitatively good, now we are talking about quantitative. And when we talk about quantitative analysis of your tooth over the time, we are talking about diagnostic tools that if you are kind of getting scanned every 6 months to predict what's going to happen in the mouth and how to prepare a better plan for you so that you don't lose a tooth. So these are some very exciting things that are going on. And I am myself and a lot of people from my lab are actually working on these very interesting ideas. So this is slightly different application, but I wanted to kind of like discuss this just to give you an idea that data science is like a lot about like getting data from different fields and then thinking about how to improve the process and how to bring new services. Before I end, I would like to end with this shameless plug that 3M is hiring a lot of data scientists. Even in this week, I learned that there are 2 positions open. So those who are in the job market are kind of looking for a place to start data science with an interesting place like 3M. I think you should check out the 3M Careers website. And feel free to approach me if you kind of have any difficulty finding these requisitions, but they are out there. So go ahead and start applying. And I would like to conclude this presentation by saying that we always kind of, the list of the tools kind of get very daunting very early on in the career. So don't worry about it. I think as long as you stay focused on the problem that you are trying to solve, with being with the right people at the right time, data science is all about collaboration. So you can go really far if you are interested in a particular problem and also interested in finding people who can help you solve the problem. So whether you are in an application side of the field or you are in computer science or statistics, I think it's about looking the other way and finding collaborations. And as Jeannie mentioned, that I have 1 year contract of being a visiting scholar with IMA Data Science Lab. So I am on campus mostly once a week, and I'm actually myself looking for a lot of collaboration where we can bring the academic side and the industry together. So talk to me if you want to kind of like learn about what I'm interested in, and I'm interested in knowing other problems. Thanks.